Good morning, everyone. Today, we will see evaporators, which are the critical devices that converts liquids into vapor by applying heat, playing a key role in thermal management. Evaporators are essential in the refrigeration, air conditioning, and chemical industries, enabling processes like cooling and concentration. In this lecture, we will explore the working principle, types such as natural or forced circulation evaporators, and application in food processing, desalination, and more. We will also discuss how their design impacts efficiency and performance. By the end, you will understand how evaporators facilitate heat exchange and why they are vital for energy efficient systems. From cooling your home to producing concentrated syrups, evaporators are everywhere. Let's get started and uncover the science behind these versatile devices and their impact on modern engineering. Let's begin with the basics of evaporators. An evaporator is a device that transforms a liquid into vapor by supplying heat, a process central to many industries and thermal systems. In refrigerations and air conditionings, evaporators absorb heat from a space, causing refrigerant to evaporate and cool the surrounding. In chemical industries, they concentrate solutions by evaporating solvents. Evaporators are crucial for thermal management, ensuring efficient heat exchange between fluids. For example, in a fin tube evaporator, refrigerant vaporizes as it absorbs heat from air, cooling it from air conditioning. These devices are used in diverse sectors, from food processing to wastewater treatment, due to their ability to handle phase change effectively. Understanding evaporator is the key to designing systems that optimize energy use and process efficiency. So let's explore their working principles to see how they achieve this transformation. The working principles of evaporators revolves around phase change. Heat is supplied to a liquid, raising its temperature until it reaches its boiling point, where it begins to vaporize. This heat can come from steam, hot fluids, or electrical sources. As the liquid turns into vapor, it absorbs significant energy, that is called as a latent heat, making evaporators efficient for heat transfers. The vapors is then separated from the remaining liquid, often collected or directed to the next process stage. In a refrigeration cycle, for instance, liquid refrigerants evaporate into the evaporator, absorbing heat from the surrounding to provide cooling. This principle is also used in distillations to separate components or in chemical process to concentrate solutions. The efficiency depends on the factors like heat supply, liquid properties, and evaporator design. Understanding this process helps engineers to optimize the evaporator for specific application, ensuring effective phase change and heat transfer. So let's move on to the different types of evaporators. Evaporators comes in various types, each suited to specific application. Natural circulation evaporators rely on density differences to drive fluid movement, offering simplicity. Forced circulation evaporator use pumps to enhance flow, ideal for viscous liquids. Falling film evaporators allow liquid to flow as a thin film over the heated tubes, maximizing efficiency. Rising film evaporators use vapor to lift liquid upward in tubes suitable for low viscosity fluids. Multiple effect evaporators employ several stages to reuse heat, boosting energy efficiency. Other designs include plate surface, tubular, and fin tube evaporators, each optimized for specific conditions. For example, fin tube evaporators are common in refrigeration, while plate evaporators are used in food processing. Understanding these types helps engineer to select the right evaporator for factors like fluid properties, scale, and energy requirements, ensuring optimal performance. So let's explore natural circulation evaporators in more details in the next slide. Natural circulation evaporators operate using the density difference between the heated and cooler liquids to drive fluid movement, eliminating the need for mechanical pumps. When liquid is heated in tubes, it becomes less dense and rises, while cooler, denser liquid flows downwards, creating a natural circulation loop. This simple design reduces maintenance and operational cost, making it popular in industries like sugar and chemical processing, where large volume of liquids are concentrated. For example, in sugar productions, these evaporators remove water from the cane juice to produce syrup. However, they are less effective for high viscosity fluids or where the scaling is concerned. As the circulation relies on the natural forces, their reliability and low energy requirements make them ideal for the application with stable operating conditions. Understanding natural circulation evaporators helps the engineers to design cost-effective systems for process requiring steady, low-maintenance operations. Next, we will look at the forced circulation evaporators, which offers certain enhanced performance. Forced circulation evaporators use pumps to actively circulate liquids through the heat exchangers, overcoming limitations of natural circulations. This ensures consistent flow, preventing scaling and fouling on the heat transfer surfaces, which is critical for high viscosity liquids or solution prone to crystallizations. The pump-driven flow enhances heat transfer by maintaining turbulence, improving efficiency. These evaporators are common in chemical industries for concentrating solutions or in crystallization process, where precise control is needed. For example, in producing salt, forced circulation prevents crystal buildups on tube, while they require more energy and maintenance than natural circulation designs. Their ability to handle challenging fluids makes them versatile. Understanding forced circulation evaporators helps the engineer to design systems for demanding applications, balancing energy costs with performance. Their robust designs ensures reliability operation in processes where fluid properties or scaling could otherwise hinder efficiency. So let's explore falling film evaporators in the next slide. Falling film evaporators are highly efficient designs where liquid flow downwards as a thin film along the inner walls of heated tubes. Heat from steam or hot fluid outside the tube causes the liquid to evaporate with vapor forming in the tube's floor. This thin film maximizes heat transfer while minimizes the temperature difference needed, making it an energy efficient. The design reduces residence time, falling, or preventing the thermal degradations, which is critical for heat-sensitive materials. Falling film evaporators are widely used in dairy, pharmaceuticals, and food industries, such as concentrating milk or fruit juices. Their high efficiency and gentle processing make them ideal for maintaining product quality. However, they require careful control to maintain the film and avoid dry spots. Understanding falling film evaporators help the engineer to design systems that combine efficiency with product integrity, especially in industries prioritizing quality. Next, we will discuss the multiple effect evaporators which enhance energy efficiency. Multiple effect evaporators improve energy efficiency by using multiple stages or effects to evaporate liquid. In each stage, vapor generated from one evaporator is used as the heating medium for the next, reducing overall steam consumptions. For example, in a triple effect evaporator, steam heats the first stage and the resulting vapor heats the second, and so on. This cascading process significantly lowers energy cost, making it ideal for large-scale applications like desalinations, where seawater is concentrated, or in the pulp industry for processing black liquor. While the initial setup is complex and costly, the energy savings justify their use in high throughput process. Understanding multiple effect operators helps the engineer to design sustainable systems that minimize energy use while maintaining high output. Their ability to reuse heat makes them important for efficient industrial process. So let's explore the applications of evaporators across various industries in the next slide. Evaporators have diverse applications across industries. In refrigeration and air conditioning, they absorb heat to cool spaces with refrigerants evaporating in the film tube or plate evaporators. In food and dairy industries, evaporators concentrate liquids like milk, juices, or syrups, preserving flavor and reducing the volume for storage. Wastewater treatment and desalination use evaporators to remove water, producing clean water or concentrated brine, critical for sustainability. In chemical and pharmaceutical industries, evaporators concentrate solutions or purify compounds, handling high viscosity or heat-sensitive materials via force or falling film designs. Molecular desalination, a specialized evaporation process, is used for high viscosity substances in pharmaceuticals. These applications highlight evaporators' role in thermal management, product quality, and resource efficiency. Understanding their versatility inspire innovative designs for cooling, concentrations, and purification challenges. So let's conclude with the summary of evaporators and their significance. To summarize, evaporators are vital devices that converts liquids to vapor, enabling efficient heat exchange and thermal process across industries. Their working principle involves heating a liquid to its boiling point with designs like natural circulation, forced circulation, falling film, and multiple effect evaporators tailored to specific needs. Application range from refrigeration and air conditioning to food concentrations, desalination, and chemical processing, showcasing their versatility. Efficient evaporator design, such as multiple effect systems, leads to significant energy savings and better performance, critical for sustainability. By handling phase change effectively, evaporators ensure product quality, reduce waste, and optimize process. Understanding their types and application equips engineers to design systems that balance efficiency, cost, and reliability. I hope this lecture has deepened your understanding of evaporators and their impact. For next time, consider how an evaporator functions in a systems you encounter, like a refrigerator or an ice plant. Thank you, and let's keep exploring heat transfer.